This is a talk given at the Nobel Symposium of the Center for the Study of Complex Systems at the University of Michigan in December 2021. I'm going to be talking about the Nobel Prize in Physics and the part of the prize that was given for climate science. In October of 2021, the Nobel Prize in Physics was awarded to Suki Manabe, Klaus Hasselmann, and Giorgio Parisi for groundbreaking contributions to our understanding of complex systems. I've been asked to speak about the underlying work of the prize, the importance of that work in the broader context. I will only speak of the work of Manabe and Hasselmann, who were climate scientists, and another talk in the symposium will cover the work of Parisi. In the citation for Manabe and Hasselmann, they were given the prize, quote, for the physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming. In order to frame my talk, I'm going to use some material from my climate change class. And I'm going to use two ideas. The first is that climate change science is characterized by simple physics in a complex system. And the second idea I want to talk about a little bit more is how do we feel confident about our descriptions of a warming Earth? And in answer to that second question, you need to look at a whole system of knowledge, a whole system of information that comes into a decision. And in climate science, and perhaps abstracted to science in general, we have observations, we have theory, we have a set of models that are focused on understanding particular processes, particular phenomena. And then in our field, we have these global models, which are considered to be increasingly more complete, comprehensive representations of the Earth's environment, the Earth's climate, which give us a way to explore the future of what our climate might look like. If we were to look at the work of Manabe and Hasselmann, their work contributes primarily to the theory part and also to the part concerning global models. Now, what we do in order to get some confidence and get some robustness in how we think about the future, if all of these pieces are consistent, so if observations and theory and the global models and the process models, if all of the knowledge and all of the ideas about the future become consistent across these, then we start to have more confidence in our ability to say something meaningful. If you think about that, one of the key aspects of science and of climate science and of the usability and the ultimate application of climate science is how do we manage uncertainty? How do we frame uncertainty, and how do we think about uncertainty? I want to start out with the idea of how simple this is in simple physics. And we all have some idea of the Earth being warmed by the sun. And the Earth sends radiation, heat, back into space, largely through infrared radiation. But if you think about what the sun does, energy is coming from the sun, and two things that can happen. It can either be reflected back, or it can be absorbed. Let's build up from this simple idea to something more complex. We've known about greenhouse gas warming since around 1800, and this was especially true for the gases of water vapor and carbon dioxide. We know that, intuitively, absorbed solar radiation, mostly visible light, heats up the surface. Heated surfaces want to get rid of that heat. If it's warmer than its surroundings, it wants to come into thermodynamic equilibrium. And one of the ways that heated surfaces get rid of some of that heat is through infrared radiation. Greenhouse gases absorb that infrared radiation. They re-emit some of it back to the surface and effectively act like a blanket and hold heat close to the surface of the Earth. We are increasing carbon dioxide as well as other greenhouse gases, and that increases the heat that's being held at the surface of the Earth. That's pretty simple. We get great complexity because of water. Water can exist as a gas, a liquid, or a solid. And the different phases of water change the absorption and reflection. Water vapor absorbs infrared energy, so it's a very strong greenhouse gas. Ice and cloud tops reflect solar energy. So they're effectively perhaps cooling the Earth because they are sending energy back to space. And that's just two examples of a very rich and complex role that water vapor plays. And in fact, if you were to think about the climate a little bit abstractly, you can almost think about it as, how much ice is there? What is the relationship between the solid, the liquid, and the gaseous phases of water? Also, as water changes phases, it transports heat. The atmosphere and oceans are fluids. They transport heat. After this, we're starting to see all the complexity emerge, and we arrive at another question. If we heat the Earth a little bit, does Earth respond by heating more? If we were then to take and build up piece by piece the Earth's energy balance, we started with this sun and the absorption and reflection, but we now have this whole complex of infrared radiation where the surface is emitting. Some of it is being captured and returned to the surface. Some of it is ultimately oozing out. Clouds have come into play, and clouds can reflect from their top and cool, and they absorb from the bottom, and they essentially behave like a barrier to heat getting out to space and to cooling. And then we mix in the complexity of the phase changes of water, and then just the transport of what we call sensible heat that you feel in a warm burst of air. And so you start to see all of this complexity emerge. So Manabe's contributions were to provide a concise, essential theory that captured the complexity of the carbon dioxide heating and the three phases of water. He used this theory to develop simulation capabilities that, one, they included this complexity of clouds and water in its essential nature. It refined the heating that would occur from the doubling of carbon dioxide. People had been thinking about the role of carbon dioxide for nearly a century at that point. It provided a defensible answer to the question, if we heat the Earth a little, does the Earth respond by heating more? The answer is yes. It included the complexity of heat transport by the atmosphere. And because of that, it started to show that heating by carbon dioxide looked different than heating caused by, for example, changes in the energy of the sun. For example, this amplified heating that we're seeing in the high latitudes in the polar regions. We build even more complexity. If we ask what happens to the additional heat, the energy held near the surface of the Earth, then the heat is accumulating and it's permeating through the planet. Of this extra heat, 89% is taken up by the ocean, the vast majority. 4% is taken by ice, much of it melting ice. 6% is taken into the land, and 1% is all that remains in the atmosphere. It's important to remember this heat is accumulating, it's stored here, and it's going to be around for a long time. We can't just say turn carbon dioxide heating off and expect the planet to immediately return to its past state. If you want to think about it a little bit differently, as this heat is accumulating and permeating the planet, where does it go? Well, there's a change in heat. That's energy. And I put here first water because, as I said earlier, we can frame our climate as the balance of water vapor, liquid water, and ice. A lot of that heat is going into water and the characteristics, amounts of water that we see on the planet. So the heat changes the physical climate, that is, the weather and the oceans. The heat is changing the chemical climate because we're seeing a changing composition and chemical reactions are heat sensitive. And we have aerosols, those particles in the air, and they're very important to climate, both in terms of direct heating and cooling as well in how they alter the behavior of the composition of the atmosphere. And the heat also ends up changing the biology. From a climate modeling perspective, life, chemistry, physics can all be viewed as energy. It's good that when we have this heat coming in, that it can permeate these things and to go through it, because we wouldn't want it all to be, say, accumulating in such a way that we might have an explosion or something like we would have if we put a unpeeled eggplant into the oven to roast it. So the heat ends up everywhere. If we just focus on the physical climate and look at the atmosphere and the ocean, these are fluids. And if you think about even the flow in a brook, then fluids are complex. And they can have this characteristic called chaos, so they might be chaotic. And you can see this idea of the complexity of the fluids in this picture of a simulation of currents in the ocean, where you see these currents and you see the waves and you see these swirls and vortices. And the ocean and the atmosphere look like this observationally, and increasingly we have the ability to simulate this. So Hasselmann's contributions were that the potentially chaotic nature of fluids does not keep us from predicting that the climate will change. The variability of the atmosphere and the ocean, which often behave as a coupled system where they're exchanging heat and other attributes back and forth between each other, can be viewed as noise above which a climate trend must appear to be detectable. The fluids will respond to the heat. They will transport the heat around, but fundamentally, they do not exactly determine the climate. That because different primary sources of heat will have different responses to that heat, we can develop patterns or fingerprints. And with those fingerprints, we are able to attribute the observed heating that we have already experienced to increases in carbon dioxide that come from fossil fuels. And the heating of the Earth exceeded the noise in about the year 2000. So what are the impact and the context? I was asked to name some names, and the names that come to mind are Warren Washington, Akiya Arakawa, Jerry Malman, Jim Hansen. And those are folks who were very early and very important in global climate modeling. And then I put Ben Santer, who has taken the concept of fingerprinting and the attribution to an elegant and sophisticated level. But I can name hundreds of people. The problem with naming some names is that you undoubtedly leave out some others. So these were just some that came to mind. The consequences of the work are enormous. They tell us the climate is warming. They frame the consequences of that warming, and they give us an opportunity, which is unique in all of history, to influence positive outcomes for humans on Earth with regard to the environment and the climate that humans will experience. I want to close with this idea of uncertainty and confidence again. If we go back to Manabe and Hasselmann, I said earlier that their big contributions were in theory and in global models. If we look at the theory and look at the warming that we expect, that the planet has warmed and will warm is so certain that we are confident to say it is unequivocal. We are equally as certain that we can attribute this to carbon dioxide from fossil fuel combustion. But if we look at the other end of this spectrum, the global models, then the uncertainty from global models that we're using to try to get some detailed look, to try to explore how the planet will change and help us to think about what might happen in ways that just based on our day-to-day intellectual capacity we aren't able to do. So these are really tools for exploration. The uncertainty is enormous from those. The consequences are also enormous. Therefore, some years ago now, the community recognized that the need to validate and to have controlled experimentation with climate models. So the community as a whole came together to design simulation experiments, standardized observations, evaluation standards, and uncertainty descriptions. Through that, this project called the Coupled Model Intercomparison Project emerged, and I just have one paragraph here from their description on their website. that CMIP, the Coupled Model Intercomparison Project, began in 1995 with a set of common experiments to look at model response to idealized forcing. Since that time, there have been increasingly more sophisticated phases of CMIP, and we're now in CMIP 6. The experiments continue to include integrations with idealized forcings and models of various sophistication. And these models are at the center of our understanding what the future is and describing the uncertainty associated with that future. And we are at a point that because of this extraordinary scrutiny that's been given to these models, that it's a defensible assertion that the projections and the evaluation of climate models have earned legal standing. An end statement. We, our field, are both delighted and, in fact, mostly surprised by the recognition of climate science by the Nobel Physics Prize. The contributions of Manabe and Hasselmann are foundational to the field of climate science, and their work continues to have influence with thousands of active researchers every single day. And finally, I want to say there are obvious political statements about the importance of climate science and climate change and the need to address climate change coming from the Nobel Committee. I thank the organizers for inviting me, and thank you for listening.